These review slides do cover everything that's on the test. Went through it and they're a little random. I sort of threw them together. Just today I didn't have review slides for the first exam in the past. I just pulled stuff out. So it's a little random. There may be some access. So let's start with stuff from Chapter 1, a quick review of the different types of tools that might apply to a single problem. UV-Vis, FTIR, NMR, mass spectrometry, gas chromatography, and liquid chromatography. UV-Vis measures electronic transitions within a molecule. FTIR measures vibrational frequencies. NMR measures the magnetic environment around each nucleus. Mass spectroscopy measures mass to charge ratio of an ion or ion fragment. And GCLC separates and purifies the analyte from a complex matter mixture. These are sort of the uses of those. So, some characteristics of analytical methods. You can make a calibration curve, which is the result of signal versus the amount of known compound or property being measured. And that allows you to describe the response and use that for future measurements. You can use the calibration curve can be, a nice linear. Generally, we're using a linear thing with a slope times the concentration plus some instrument signal for blank. And so if you've eliminated the blank, it's just slope times concentration. And there can be an issue with selectivity. I don't have a question about selectivity. Some limits of detection. Signal to noise ratio is important. It's the net response recorded by a method for a sample. You want to have a signal to noise ratio better than 2. Dynamic range, that is sort of a limit of quantization, which is sort of the lower end of the range, and the limit of linearity where it stops being linear. So, electromagnetic radiation is the primary thing we're looking at. We're looking at the absorption of electromagnetic radiation. So there's a number of questions about electromagnetic radiation. So spectroscopy is a method of analysis based on the interaction, absorption, and production of light by matter. Light is electromagnetic radiation. You can look at it with a wave model or a particle model. With the wave model, it's represented as a sinusoidal wave with a wavelength and an amplitude. The wavelength is a distance in nanometers, centimeters, and meters from peak to peak. Wave number is 1 over the wavelength, and the units is always in inverse centimeters. That's the standard unit used for wave number. So remember that wave number is inverse centimeters. You need to keep track of units, and it's 1 over the wavelength. And it's written as V bar like that. Frequency is the number of cycles or oscillations per second. That's in hertz or inverse seconds. And the velocity is equal to the frequency times the wavelength for any wave. For light, maximum velocity is c, the speed of light in a vacuum, which is 3 times 10 to the 8th meters per second. It is slower in other media. It's about 0.03% slower in air. And it's significantly slower in, say, glass. I mean, not hugely slower, but it's about 1.5, a factor of about 1.5. So, wavelength, frequency, and energy. Speed of light is wavelength times frequency. That's an important relationship that will show up. So these equations are important. And energy is Planck's constant times the frequency, or Planck's constant times the speed of light over the wavelength. So If you have a wavelength, Planck's constant, and so if you have the frequency, to find the energy, it's Planck's constant times the frequency. If you have a wavelength, it's Planck's constant times the speed of light over the wavelength. You need to keep track of units. And for if you have a wave number, it's Planck's constant times speed of light times the wave number. But again, you need to keep track of units. Because wave number is always going to be in inverse centimeters. But the speed of light, the standard is in meters per second. So you might have to do a conversion. And then when it slows down, this is where the index of refraction is the ratio of the speed in a vacuum to the speed in the material. The bigger the index of refraction, the slower light moves in it. Particle model, you can think about light as discrete particles of energy called photons. And when they interact with matter, they execute a transition between two energy levels. That means that the energy of the photon corresponds to the energy hv or h nu corresponds to the difference in energies for the transition. Proportional to frequency and wave number, it's inversely proportional to wavelength. This is the electromagnetic spectrum with the various bits of it labeled. This lab we're primarily going to be dealing with infrared. This test we're primarily going to be dealing with infrared. There's refraction. When a wave enters a medium where it travels at a different speed, it bends. That bending is described by Snell's law and the index of refraction, where the index of refraction times the sine of the angle to the normal equals the index of refraction times the sine of the angle to the normal. Don't think I actually have you do any Snell's law calculations, but the fact that the index of refraction varies with wavelength is how prisms separate light into various colors. So this is Snell's law. And the index of refraction is medium or substance specific. So here are some indexes of refraction. Can't remember. I might have something about finding the speed of something with an index of refraction. I might be remembering a question from a test from another class. Like I know I have that question on another class. So, but the values of index of refraction are wavelength dependent, which is important for prisms, because prisms will separate them out. And if they're in a table, they're usually given for the sodium double line at 590 nanometers, because that's a very easy monochromatic light to get. Light will diffract. When it goes through a slit, it will bend around the slit. It is more pronounced when the size of the slit or opening is approximately the same size as the wavelength of the light. So the ratio of the wavelength of the light to the size of the slit is what's important. And the closer they are in size, or if the slit's smaller than the wavelength, it can have pretty big effects. A wide slit, minimal diffraction; thin slit, lots of diffraction. Waves superimpose, they add up. You have multiple waves, they will add up. This leads to the potential for interference. There are two types of fundamental. Now, waves can either add up constructively, where they're in sync with each other, so they make a bigger wave, or destructively, where if they're out of sync with each other, if they're out of phase with each other, they can cancel out. And this interference process can create patterns. because if you have different distances, so this can filter. This is how actually blue eyes become blue, and other things like that. Interference patterns can. So destructive interference can occur when two waves from the same source travel different paths to get to a point. And if those paths differ by half a wavelength in length, they will cancel. If it's a whole number of wavelengths, they'll add up. And this principle of interference, based on the path difference, is used in a lot of things. So if you have more than one slit, you get a series of high and low intensity regions in an interference pattern, like so. And if you have, or if you've seen rainbows, rainbows are formed via interference patterns as well. And you get multiple rainbows from an interference, the interference pattern. And the order of interference and times the wavelength is d times the sine of the angle, where d is the spacing between the sets and the angle, but the angle between them. So this proves that light is, you can do this experiment to prove that light is a wave, and you can calculate this. So we're talking about absorption. Energy is absorbed. The energy that gets absorbed corresponds to the difference in energy between various energy levels. Atomic absorption tends to be simple. Molecular absorption is more complicated because there's a whole lot more ways that there's a whole lot more energy levels. Here are the quantized energy levels associated with molecular vibration for a diatomic molecule. General idea for vibration, it tends to be a simple harmonic oscillator. So the energy levels are some fundamental frequency times n plus a half, starting at 0 and going up. So the absorption for electromagnetic light energy gets transferred to atoms, ions, or molecules in the sample. There's a transition to a higher energy state, and the difference in those energies corresponds to the energy of the photon. And that can be a change in energy levels, vibrations, rotations, translation, etc. For IR, it's generally vibrations. To study this, we look at the power, the energy of a beam that reaches a given area per second, and the intensity of power per unit solid angle, which is related to amplitude squared. And a most important tool is Beer's law, which is that the absorption, the light absorbed by a sample, is dependent on the path length, the concentration of the sample, and the proportionality constant, which is the molar absorptivity. And the amount of light absorbed is dependent on the frequency or wavelength, but in the problems, you're looking at one frequency or wavelength. So for example, if you have a solution that's 3 times 10 to the minus 3 molar in X with an absorbance of 0.2 when measured in a 1 centimeter cell, what concentration of X would be required for the absorbance to be increased to 0.6 when a 1 centimeter cell is used? So here the trick is that because you're dealing with the same substance, and absorption equals epsilon BC, A over BC equals epsilon, and that means that A1 over B1 C1 equals A2 over B2 C2, and B is the same in both cases. So you get A1 over C1 equals A2 over C2. So So C2 equals C1 times A2 over A1, and then you can solve for C2. Knowing a starting concentration and absorbance. And similarly, I'll tell you right now on the test, I don't think I'll change the cell like that. So this is Beer's law. Now to get absorption, there is transmittance, which is the power. The transmittance is the power observed divided by the power with nothing. So P naught. And so it's like the percentage of the total light that would happen if there wasn't a sample there. And absorbance is log base 10 of P0 over P, so minus log base 10 of transmittance. And there are questions about converting absorbance to transmittance and vice versa. So if no light is absorbed, transmittance is 100%, absorbance is 0. If all light is absorbed, transmittance is 0%, absorbance is 1.
Like the negative inverse log?
Yeah, so like I give you a transmittance and I ask you what the absorbance is, or vice versa.
So you just do the negative log?
So if I told you the transmittance was 20%, you do minus log base 10 of 0.2. And that will give you the absorbance. Or if I told you the absorbance was 0.5 and I wanted you to find the transmittance, you could do it the other way around.
But then what did we talk about?
It's e to the minus absorbent. Well, it's 10 to the minus absorbance power gives you transmittance. Sure. So let's say absorbance is 3. Let's go with. Let's say you have 3. You want to figure out what transmittance is. That's absurd. That's outside the range you'd normally expect. But I just want to do a nice round number.
You're gonna find transmittance, right?
Yeah, I'm going to find transmittance. Well, absorbance is equal to minus log base 10 of transmittance. So if I solve for transmittance, minus absorbance is log base 10 of transmittance. So 10 to the minus absorbance is transmittance. That's how you get rid of log. And so 10 to the minus 3 is transmittance. So 10 to the minus 3 is 0.001 or 0.1%. I mean, yeah, not going to give you an absorbance of 3 is outside of the healthy range. Generally, your healthy range for absorbance is up to about 1-ish, because 1 is about 10% transmittance and below about 10% transmittance. Starting 0.1 is 80, around 80%. That's fine. It's just that if your absorbance is more than 1, your transmittance is less than 10%, which means you've got very little light passing through, so it's very easy for noise to wipe it out.
Okay.
That's all. I mean, 0.1, like we were working with absorbances that were less than that were fine. So I think there was some math errors in that caffeine. Oh, I got the caffeine lab. Oh, you have. Okay, yeah. No worries. You can give it to me then or next week or on Thursday.
Okay.
But yeah, so this is absorbance. Absorbance is what is proportional to epsilon B concentration. So if you have a problem about that gives transmittance, so you have to convert to absorbance, like here. So here has a transmittance, and we want to increase the transmittance by a factor of 3.
So how do you know when to do it? Giving you something.
Well, yeah, so the thing is that Beer's law is always proportional to absorbance. So if you want to do calculations about concentration with Beer's law, you're going to need to convert to absorbance. Well, this gives you transmittance. And it says it's transmit. That's how you know it's transmit.
Yeah. This one will be the.
Well, I mean, they give you transmittance. They tell you that transmittance is going to be in fact increased by a factor of 3. So what you're going to do is you're going to convert transmittance to absorbance with this formula. So transmittance 2 is 3 times transmittance 1. So transmittance 1 is 0.212, transmittance 2 is 0.636. So here's our formula. We know B is the same in both of these. So A1 over C1 equals A2 over C2. So C2 equals C1 over A2 over A1. A is minus log transmittance. So A1 is going to be minus log of 0.212, which is that. And A2 is minus log of 0.636, which is that. I mean, these are in the slides. So.
Yeah, it did pop up on my phone.
I did just put it up today, but it should be visible. And these are also in the old. All I did is copy slides out of previous existing ones. Nothing is new here.
Like, it like wasn't going through the, that makes sense, like if you share, like make it full screen, if you like press the button, it wouldn't like all pop up.
Let me just check that I made it visible. I'm pretty sure I did, but.
No, I just copied it off. But it's not popping up.
Go to the next slide.
Next slide.
Yeah, I made 2 slides for this one. This is 2 slides. That one I can tell you the problem was that I separated the answers onto a second slide.
Okay.
Go to the next slide. That's what it was. And then you would just do the ratio. And you get the answer. Then a monochromator is some wavelength selector. You separate specific frequencies from polychromatic light. It only allows certain wavelengths to be selected and used. A dispersing monochromator is some monochromator based on separating out wavelengths, spreading them apart, and then choosing a slice of them, basically. So you can use a prism that uses the refraction of light and the fact that different wavelengths have different refractive indexes, spreads those out. Because the refractive index changes as a function of wavelength. So down in the visible here, you can see there's quite a bit of change in the refractive index. That lets that light range spread out. Doesn't work so well in the near infrared because of Snell's law. the light has to hit the prism at an angle, and the most common is the 60-degree prism. You can also use a grating monochromator that's based on diffraction of light and constructive and destructive interference that separates light via interference effects, and different wavelengths have constructive interference at different points, and that separates out. And you can select desired wavelengths by letting light at different points into the instrument. Same principle on both of them. You can separate light by letting light at different points into the instrument. And then the reflection grating is the most commonly used version of diffraction grating, which is a grooved surface with a reflective coating. If you've ever seen one of those holographic foil things or like stickers, that's effectively what's going on here. That is a refractive grating. It's not a very like great reflective grating, or a CD. CDs do the same thing. But something reflective that you see rainbows on, probably effectively a reflective grating. I don't think I asked any questions about the exact formulas here, but here's how you do this. And gratings versus prisms. Gratings have a uniform dispersion versus wavelength. They're smaller, but they have higher stray light, but they work for all wavelengths. While prisms, shorter wavelengths are better separated. They're larger. Stray light is less of a problem, but they're limited in the range that you can use them in because they're made of material that absorbs light. And increasing the size of either the prism or the grating will give you better dispersion. Stray light can be removed with filters, and glass absorbs light at less than wavelengths of 350 nanometers. The other method that we use to separate wavelengths is interference-based, which is time domain versus frequency domain using the Fourier transform. We use FTIR, where we convert the interference patterns into frequency information. So this is a time domain plot as we vary the position of one of these legs in a Michelson interferometer, and then we can convert it into a corresponding frequency. So this is, the sum of two waves that vary in time gives you, with different wavelengths or different frequencies, their sum, and you can separate them out into the individual frequencies. So this is a time domain measurement, looks like this. And we can separate it out into the individual frequencies using a Fourier transform. So Fourier transform advantages over dispersive information instruments. The collection times are faster. You get a multiplex advantage because you're collecting all frequencies at the same time. You can also do a throughput advantage because they're faster. You can take a lot more measurements to increase signal to noise ratio. And they tend to have better resolution. So usually they use something like a Michelson interferometer with a movable mirror and a fixed mirror. And as you move the mirror, this changes. You get a wave that occurs as a function of how many wavelengths you are from the center. As you move the mirror back and forth, and so that gives you basically time domain information that you can turn into frequency information. So this is sort of a schematic of FTIR with a Michelson interferometer. You have a pulsing mirror, a stationary mirror. This light then goes through the sample, and then you have the optics in the detector. And this is, plot of power reaching the detector as a function of the offset of 0. And that, because of interference, corresponds, to a specific wavelength, and you get that information on. So the advantages, they have better resolution. The Michelson interferometer resolution equation is this. So the resolution is proportional to how far your mirror moves. Well, it's proportional 1 over how far your mirror moves. So the further your mirror moves, the finer a resolution you have, basically, which is great because it's easy to move a mirror a little further. And so here's some examples of waves and the corresponding frequency information. So this is the time domain, basically, and this is the frequency domain. And this sort of Fourier transform thing is incredibly useful and gets used all the time. So we'll be using similar Fourier transform based things in other methods of study. So we look at an infrared spectroscopy. Generally, you're looking at the vibrations of molecules. So IR radiation is frequencies between 10 to the 12 to the 15 hertz. Wavelengths between 10 to the minus 6 to 10 to the minus third. Wave numbers between 10 and 10,000 inverse centimeters. Remember that wave numbers are inverse centimeters, so you can't just take whatever the wavelength in meters. You have to convert it to centimeters. And primarily what we're looking at is vibrational transitions. So vibrational transitions have the nice effect that there's both vibrational and rotational. We're primarily looking at vibrational transitions here. The potential energy looks a lot like a harmonic oscillator. And that's nice because the harmonic oscillator has a really nice energy equation for the energy levels. Infrared radiation is between 12,800 and to 10 inverse centimeters. Rotational transitions have small energy differences. Vibrational transitions occur at higher energies. And rotational and vibrational transitions often occur together. There's an IR spectrum for an organic molecule. Energy is H times frequency, or H bar C over wavelength. So typical IR spectrum, many more bands than UV vis. Bands are much sharper. It's a good qualitative tool. You can also use it as a quantitative tool. I think the harmonic oscillator model says that the energy is like 1/2 ky squared, where y is the displacement. When you take that energy well and apply quantum mechanics to it, well, just if you do classically, it has a vibrational frequency of 1 over 2 pi times k over mu, where mu is the reduced mass. And if you know V and the atoms in the bond, you can get K. And so single bonds, double and triple bonds are about 2 to 3 times the K of the single bond. The vibrations occur single, double, triple. And the energy levels, the vibrational frequency is 1 over 2 pi K over mu. Turns out the energy levels for a quantum harmonic oscillator are V plus 1/2 times H bar over 2 pi K over mu, which is just why did I circle with those seem weirdly placed? Oh, I think I know what happened. Stuff got messed up because this got converted from 3 by 4 to 16 by 9. But the important thing here is that, you know, energy level is V plus a half times H times that natural resonant frequency. But that means that the difference in energy levels is just, you know, the 1/2 cancels out and you get the difference. So it's just, from 0 to 1 is H bar times Vm, from 0 to 2 is 2H bar times Vm, and so on. So the frequency is that, and then there's the wave number. But the idea is that if you're going from 0 to 1, it'll be something, 0 to 2 will be twice the frequency, 0 to 3 will be 3 times the frequency. And if you have not particularly high vibrational quantum numbers, you get anharmonic oscillations where those you get less, stuff gets weird. But you don't need to deal with the actual anharmonics. You sometimes get 2 or 3 delta V plus 2 or plus or minus 2 or 3, which observed you get overcome lines. And the types of molecular vibrations, there are symmetric. Bond stretching can either be symmetric, where they both go out and in, or asymmetric, where one side goes in, the other side goes out. When you have bending, it can be rocking, scissoring, wagging, or twisting. So here are some animations of those. And here's some other illustrations of those. These are the stretches, the asymmetric stretches. There are the bendings for CH4. For nonlinear molecules, the number of types of vibrations is 3n minus 6. For linear molecules, it's 3n minus 5. This is why there's so many peaks in IR spectra. Observed vibration can be less than predicted because of symmetry, where there's no change in dipole. Or you could have the energy levels of the vibration being identical. That's degeneracy. Or the absorption intensity can be too low, or the frequency is beyond the range of the answer. So for example, HCl has 1 mode, it can stretch. CO2 has 4 modes, but only modes which change the dipole are active. So the bottom 3 modes are the only ones that are active. And 2 of those are degenerate. So here, CO2 has 4 modes. That one's IR inactive. This is IR active. These 2 are IR active, but they're also degenerate with each other because they're basically the same vibration, just in different directions. So they have the same energy. Here's a table of group frequencies for organic functional groups. So given a peak, you can guess what group it should be. And what it corresponds to. So that's qualitative analysis. Then for compound identification, you can examine what functional groups are there. And you can have the table. And then there's a really big table in both. But this table should be enough. And I included it. And here are some of the ranges for the various functional groups, where to expect them. Here's some more characteristic frequencies and some tables, just for reference. Fourier transform IR is an alternative to normal IR. It's based on the Michelson interferometer. Light from the source gets split by a central mirror into two beams of equal intensity. They go to two other mirrors, reflected by the central mirror, recombine and pass through the sample to the detector. So the sample here and detector. The two side mirrors, one is fixed, the other is movable. As you move the second mirror, light and two paths travel different distances before they recombine. This causes constructive and destructive interference when they combine. And as the mirror is moved, you get a change in the signal. So, and then to know where the mirror is, you send a laser of a known wavelength, of a known frequency or wavelength through the system, and you observe the laser, and its interference tells you how the moving mirror is moving. So that's why they all have a helium neon laser in them. The destructive interference is created when two waves from the source travel different paths to each point. When they differ by an integer number of wavelengths, the waves will be in phase. If they differ by an odd multiple of half a wave, then the waves will be 180 degrees out of phase and cancel out. And this sort of interference method can be used to do things like, so one of the things we're doing, literally one of the things in an FDIR, we're measuring how that moving mirror is moving. You want a really fancy version of that. That's how we detect gravity waves. It's a really big version of that, as in the arms are like over a mile long each. And you're looking for the length of one of them changing because of distortion of space-time from a gravity wave. And the amount that it changes by is less than the size of a proton. It's ridiculously accurate. Yeah, so basically you observe a plot of intensity versus distance. That's the interferogram. You convert it to a plot of intensity versus frequency by doing a Fourier transform. This is the calculus version of a Fourier transform. The actual way it's done is the fast Fourier transform algorithm for doing a discrete Fourier transform. Well, we definitely don't need to go into that, other than that algorithm is a really cool trick and is worth looking at if you're interested. It's not going to be doing anything like that. I would never ask you to do it anywhere near by hand. It is beautiful because it is very easily machined up. You know, automatable, not because it's something you'd ever do by hand. And then the resolution, delta V is 1 over the interval of the distance traveled by the mirror. And so to get a finer resolution, you just move your mirror further. Which is why really high-end instruments have really long tube the mirror to move in. Been watching some videos about someone putting back together and hooking up a old, really high-end IR thing. And the advantages of FDIR compared to normal IR, it's much faster, seconds versus minutes. You can use signal averaging to increase signal to noise ratio, which is great. It doesn't take a lot longer to just take a bunch of measurements and average them. Higher inherent signal to noise because there's no slits, there's less optical equipment, and there's higher light intensity, and it has a high resolution. Disadvantages, it's single beam, so you have to collect a blank. You can't use thermal detectors, they're too slow. So you have to use fast detectors. And in normal IR, you scan through the frequency range, and FDIR, you basically collect all frequencies at once. And that's the end of the review. Any questions about anything? There are 10 questions on the exam. I just checked. They're a mix of like short answer questions and calculation questions. Yeah. And if that's your lab, yeah. Okay, well, I'll see you guys on Thursday for the test.